All right, good evening, everyone. This is day 2 of week 22. Today we will be getting into self-RAG patterns with Bedrock and CI/CD pipelines. So as always, we have one lesson, one lab, one challenge. We have our TLOs and ELOs. So let's go over the TLOs real quick. We will implement self-RAG and corrective RAG patterns using Bedrock for document validation, answer grounding, and automatic correction. Build CI/CD pipelines with GitHub Actions that automatically test RAG quality and catch regressions before production. For ELOs, we have explain why basic RAG fails silently with irrelevant documents and unsupported claims. Implement document relevance validation using Bedrock with low temperature scoring. Build answer grounding validation that detects hallucinations and unsupported claims. Create corrective retrieval that rewrites queries and retries when initial results are poor. Implement query decomposition that breaks complex questions into simpler sub-questions. Add conversational memory that tracks history and expands follow-up queries with context. Implement memory summarization to reduce token costs in long conversations. Write automated test cases that verify RAG quality against minimum score thresholds. Create GitHub Actions workflows that run tests on push, pull requests, and scheduled triggers. And then finally, store AWS credentials securely using GitHub secrets for CI/CD Bedrock access. So yesterday, you built advanced retrieval with query transformation and hybrid search, but here's the problem. Your RAG system doesn't know when it's wrong. It retrieves documents and generates answers confidently, even when the document are relevant or the answer is unsupported. Today, you'll learn self-RAG and corrective RAG patterns that validate outputs, CI/CD pipelines that catch regressions automatically, and conversational memory that makes multi-turn interactions natural. What are we trying to accomplish? We aim to transform your RAG systems from generate and hope to validate and verify while establishing automated quality assurance. By the end of this session, you will understand how to validate retrieved documents for relevance using Bedrock, verify that generated answers are grounded in context, implement corrective retrieval that fixes poor results automatically, set up GitHub Actions for continuous testing, and add conversational memory that enables natural follow-up questions. You'll build systems that are both self-aware and continuously tested. Any questions before we get into the actual lesson? All right, let's go ahead and get started. All right, so self-RAG patterns with Bedrock plus CI/CD pipeline. We already went over the overview. Yesterday, you guys built advanced retrieval with query transformation and hybrid search. Today, we're going to be adding on to that. So the self-validation problem. Your day one RAG system retrieves documents and generates answers, but has no way to assess its own quality. What basic RAG does, retrieves top K documents, generates confident answers, returns results immediately, and treats all queries the same. So what's missing with when basic RAG retrieves top K documents? It doesn't check if they're actually relevant. When basic RAG generates confident answers, it doesn't verify answers are grounded in context. When basic RAG returns results immediately, it doesn't retry when retrieval fails. And when basic RAG treats all queries the same, it doesn't decompose complex questions. So let's take a look at the example. A user asks, how do I prevent overfitting? Your system retrieves a document about Python programming. So that's semantically similar to machine learning topics, but it's irrelevant. And it confidently generates an answer, mixing real knowledge with hallucinations. The user has no idea that the response is unreliable. Self-RAG patterns solve this by making your system introspective, using Bedrock to evaluate its own outputs before returning them. So for a self-RAG architecture, self-RAG adds validation checkpoints throughout the RAG pipeline. Instead of blindly trusting retrieval and generation, the system asks Bedrock to critique each step. So let's take a look at the pipeline. You have your query. It retrieves and then it validates their relevance. It'll filter out the bad documents. It'll generate, and then it'll validate the grounding. It'll flag unsupported claims, and then you will finally get your response. So for the checkpoint, we have that validate response. What it checks is each document relevant to the query that you gave it. The action on failure, so it filters out irrelevant documents. For grounding validation, is the answer supported by context? And then the action on failure is it warns the user or regenerates. And finally, for confidence scoring, it checks how certain is the system. And then the action on failure is it adds uncertainty markers. So within this first code snippet, we have a document relevance validation. Before using retrieve documents, ask Bedrock if they're actually relevant. So we have our imports. We're importing Boto3. We specify our runtime using the US East 1 region. And we finally have a function called validate relevance. We're passing in our query, which is a string, and then our documents, and we should get an output of a dictionary. So our doc string says use Bedrock to check if a document is relevant to this query. And following that, we have a prompt, evaluate if this document is relevant to answering the question. For our question, we give it our query. For the document, we give our document, and then we're telling the LLM how it should respond. So the formatting, respond in this exact format. So we want whether it's relevant, and then the reason for it. Following that prompt, we have a response. So we're invoking our model using .converse. So .converse is the API method that sends a conversational request to a foundational model and returns the actual model's response. So underneath, we specify our model. We're using Nova Lite. And this messages line right here is just providing the chat message format. So it'll say user, and then it'll have like a colon, and then we have our prompt. So uh, we're telling the LLM evaluate this document. Following that line, we have the inference config. So we're just specifying our tokens, and then our temperature, we're setting it to 0.1. We're specifying it to 0.1 so that we have a low temperature, which makes the validation consistent because we want a deterministic yes or no answer other than creative interpretation. So once we get our response, we're going to parse through it to get the text, so the answer, and then we'll save it to our variable called result. Now this variable called is relevant is just uh, it's just trying to check to see if hold on 1 second. It just extracts whether the answer is was yes or no. And then same thing for the reason. It's just extracting the reason for that answer. And we will return whether it's relevant and then the reason for it. Any questions on this snippet right here? So
Here,
yeah, go ahead, Cam.
so really, you're just adding a step of using an LLM to verify whether the documents are relevant to the question, right?
Yep, exactly. Yep.
Okay.
So that's what this function does. Later on, we'll have so we're gonna be looking at different functions that does different things, but then at the end we'll have one main function that pretty much combines all of these to have your RAG pipeline. So after we uh find out if the document is relevant, we're going to be filtering the retrieved documents. So we have a function called retrieve with validation. It just retrieves documents from a vector database, then uses an LLM through the previous function to filter out irrelevant documents. So we're passing in our query, our vector store, and then our K. So can continuing on, we have a variable called candidates. So candidates performs vector similarity search. Uh, Notice how K over here gets multiplied by 2. And again, remember, top K is selecting the highest scoring results from a set of possibilities. So we're multiplying it by 2 because some will likely be filtered out later by the LLM. So if K equals 5, for example, then the system will retrieve 10 candidate documents instead of 5. Next up, we have two lists. We have validated and rejected. So validated are the documents that are confirmed to be relevant, and then rejected are the documents that the LLM rejected. We have a loop. Uh, Next up, we have a loop. So it just loops through all the different candidates. And then, so it goes through the loop and evaluates each retried document. It will then, ask the earlier function, so validate relevance, uh, if the document is relevant. So if the so we have our result right here. We're checking to see if it's relevant or not. If the result is relevant, then we'll append it to the validated variable. If it's not, then we'll append it to the rejected list. And then we also have the reason within the rejected list, but for the validated, we just have the actual document. So within that loop, it says stop once we have enough validated docs. If we take a look at K up here, our default is 5. So if it's once we reach 5, then it'll just break. And we will return the documents that are validated, the documents that are rejected, and then validation rate, which takes the length of the validated, or yeah, the length of the validated, and then divides it by the length of the candidates. And that's just giving a percentage of retrieved documents that were actually relevant. Any questions?
Yes, Eric. Is the validation based on the LLM's determination, or are we throwing any criteria in for determining validity?
Yeah, it's based on the LLM's uh, determination. So later on, we'll have some test cases. It'll say things like expected keywords, things like that, and that's what it'll use. It'll take a look at how many of those keywords are within those documents and etc. to make its final determination.
Yeah, thank you.
Yep. All right. So let's take a look at the example. So we give this function retrieve with validation, a query. So our question says, how do neural networks learn? We retrieved 6 candidates, validated 3. For the first one, it says back propagation adjusts weight based on error gradients. Second one says neural networks use gradient descent to minimize loss. So those all deal with neural networks. So they have been validated. but the next one gets rejected. So it says Python is a popular programming language, and the reason it got rejected is because it's about programming languages and not neural network learning. We have our third validation. Learning rate controls the step size during training, which involves neural network. So that makes sense to get validated. And then the next two get rejected. It says machine learning is a type of AI. The reason is it's too general, doesn't explain how networks learn. And then the last one says data pre-processing improves model accuracy. And the reason for that is it's about data preparation and not learning mechanism. Any question before we move on to answer grounding validation? All right. So after generation, verify the answer is supported by the retrieve context. If we look at our doc string, it says check if the answer is grounded in the provided context. So for this function, validate grounding, we're passing in our query and then context and answer. We have a prompt that we specify that says evaluate if this answer is fully supported by the context provided. We give our context, and then we have our question, so our query, and then answer. We say respond in this exact format. So we have three criteria: grounded, unsupported claims, and confidence. For grounded, we have fully, partially, or not at all. Unsupported claims, it just lists any claims not found in context or none. And then confidence, we have high, medium, or low. After we specify our prompt, again, we're invoking the model to get our response using Nova Lite, and then specifying the chat format. And we specify the max tokens and temperature. Again, temperature is at the lowest, so 0.1, so that we can get deterministic answers. And then finally, we have a result. So we're just parsing that response to get that text, that output. And grounded is just parses the result and checks if it contains the word fully, or checks if it contains fully or not. And then we return fully grounded. So either for grounded, we'll either get fully, partially or not. And then we have our raw evaluation, so it's just the output itself. If you have any questions, feel free to just stop me and ask away. So for the complete self-rag pipeline, we have a function called self-rag pipeline. We're passing in our query and vector store. Our doc string says self-rag, retrieve, validate, generate, and verify. So for step one, we're retrieving and validating the documents using our function that we saw earlier, retrieve with validation, where we pass in the query, vector store, and the K. And we're setting it this time to 3. So for the if not retrieval document, so if it couldn't find any documents, or if none of the documents were validated, then it'll just go ahead and straight away return this answer. So I couldn't find relevant information to answer this question. Confidence is low, and there were 0 documents used. Otherwise, it'll continue on. So we have the context, and it'll generate an answer. Hold on 1 second. So for step two, we have a prompt. It says answer the question based only on the provided context. If the context doesn't contain enough information, say so. So we give the context, and then we have our question, so our query, and then we leave room for our answer. So for context, it says we're joining. Uh, we're joining all the content within each document inside those validated documents. So we're just giving everything that's stored within those validated documents and passing it in so that the LLM could have something to work with. Does that make sense? If doesn't make sense, just speak up and I could try to uh explain it further. All right. So after we create our prompt, we have our again we're invoking the model, Novalite. We have the messages and then the inference config. We have our answer variable. We're just parsing through the response to get the text. And then we have validate grounding. So we're calling that function, validate groundings, passing in our query, context, and answer. And then we're determining the confidence. So uh, if the grounding fully grounded, so confidence will be high if the fully grounded grounding fully grounded. Let's go back to that function. So if fully was true, it would get stored over here, is what it's saying. So if we go back down over here, if it's true, then the confidence will be high. El else it'll be medium. And then if the validation rate is less than 0.5, so less than 50%, the confidence will be low. Does that make sense? Or should I clarify it some more? Or clarify it better?
This be an example of LLM as a judge?
Mm. So say that again?
Would this be an example of LLM as a judge?
Yeah, yep. So yeah, so it would pretty much or actually the way it works is notice how in this validate grounding function we have we tell the LLM that we want it in an exact format. So we have grounded, unsupported claims, and a confidence. So it would make sense that when it returns an output, it'll immediately determine if it'll specify whether it's fully uh, grounded. So this code looks for that word fully, and if it finds it, then it'll set fully grounded as fully. If it doesn't, then it will be uh, partially. Now for the not, it's going to take in account the raw evaluation score as well. So if it's less than 50%, then it'll be uh, not grounded. Does that clarify it a bit? Okay. How about everybody else? You guys understand that part?
Was this guarding against creativity? Like temperature?
What do you mean by that?
Well, so evaluate if this answer is fully supported by the context provided. Uh,
Mhm.
so assuming, and I liked Nick's term, LLM as a judge, that the judge calls it fully fully grounded, then there's a high semantic relationship. But if it's not, then semantically it's made some stuff up maybe, or it's, off its mark.
Mhm. Yeah,
And
so
that's typically on the like temperature axis.
yeah, so we're setting the temperature to be zero point 0.1 so that we don't because we don't want it as we don't give want to give it any creativity. So we want everything to be deterministic. So from this prompt, we're checking to see if it'll respond back with the word fully pretty much is what this code is doing. So if it sees the word fully, then it's going to be it's automatically gonna append it to that fully grounded. So it's gonna return fully. But then if it doesn't see fully at all, it's just gonna be it's going to be partially to get
What do
that.
you think?
Mhm.
Yeah, what do you think is an example of it not seeing it?
Uh,
Like what went wrong?
so maybe for if it's fully grounded, it'll say something like uh judging from the context you gave me, I see that let's go back to over here. I see that uh the context mentioned or fully scored. So say for our context, we have these three that were validated: back propagation, adjust weight, neural networks use gradient descent, and then learning rate controls the step size. Uh, it will take a look at uh, those validated documents and it'll compare it uh, to the query. So if it I'm trying to think of a good example for this. So it might say something like, you know, this answer fully supports your question due to these three things. And then if it might not say fully afterwards. So for the second example, for a partial, it might say something like uh, based on the context you gave me, uh, back propagation and neural networks relate to your question, but it also mentions Python is a popular programming language, so it's not going to use fully in that sense. So it'll be partial because it doesn't see that word fully. So really, all this is a much like a simpler code. I wouldn't set it up this way. I would create some, think of some edge cases and modify it. But this is just for an example. So if it doesn't see that word fully, then it'll be partial. But now to get that, if it's not grounded, it's going to take account using the raw evaluation score. So like the uh or not, yeah, or not validation score, but validation rate. So yeah, validation rate is just the percentage uh that it let's try to find that validation rate. So say it looked at 10 documents and only four of them got validated. So that'll give you a score of 40%. So it'll say it's not grounded due to that low score. Does that make sense? So pretty much this uh the self-RAG pipeline is taking account all those previous functions we did and making a judgment based on the different components and criteria that the LLM found. You're muted, Troy.
A piece I didn't realize was we had already, like, this is coming in after we had already managed our content, came up with an actual answer, and now we're using what we had used for the content with and the answer to evaluate. So we're on the post, we're building on maybe what we did yesterday.
Yeah, so if we go through the self-RAG pipeline function again, so for step one, we're calling that retrieve with validation. So if we go back to where is it at? So we're just going through the documents and validating or rejecting them. So say we're looking at 10 and say for this initial example, maybe we got 6 validated and then 4 rejected. So we have a validation rate of 60%. And then let's go back to that full pipeline. So this part right here says if there were no documents validated at all, uh, we'll just get this back and it'll stop everything. So we'll say I couldn't find relevant information to answer this question. Confidence is low, and then 0 documents used. And then if we did find, so if we do have those 6 validated documents, it's going to take all the content from each one, join them into a string, and we'll pass it to this generation prompt. And then we'll also give it our question and then leave room for the LLM to answer.
Okay, you pieced it together for me. Thank you.
And then I'm just gonna keep going to if it's not making sense as well for anybody, just if you still need me to clarify something, just let me know. So after uh after we created our generation prompt, we're gonna invoke our model and give it the model ID, messages, inference config, and then we'll get our answer by parsing through the response and getting that text portion of it. Now for step 3, we have the answer. So we're checking to see if it's grounded. So we're getting that function, validate grounding. We're passing in our query, context, and answer. So let's go to that function, validate grounding. So we'll check if the answer is grounded in the provided context. Our prompt says, evaluate this if this answer is fully supported by the context provided. So again, our context is from all those is from all the content within those validated documents. So we're passing it again over here. We're providing our question again. and then we're providing the answer that we received. And we're also specifying the format that we want it in. So the way that this function works, specifically the validate grounding, is checking to see if the word fully is in there. So it'll check it, and then if it is, it'll set fully grounded as fully. If it doesn't have it, it'll say partially. And then we have our raw evaluation, so it's just the result that we got from invoking that model again, specifically within this function, validate grounding. And then let's go back to the self-RAG pipeline. Uh, so now we have a uh, we have a snippet that determines the confidence. So if the if the fully grounded is fully, then the confidence will be high. Because remember, or not remember, but in this validate grounding uh, function, it's just saying if fully is true. So that's pretty much what this is saying too. If it's true, confidence will be high. Otherwise, it'll be set as medium. And then to get a confidence level of low is also going to take account of that validation rate from where is it at? From the retrieved validation function. So with my initial example, I said, what if there was 6 documents validated and then 4 rejected? Since the score is over 0.5, so we got 0.6, it'll leave it as medium. But say we had so let's say only 4 documents got validated and then there were 6 rejected. We'll have a score of 0.4. So that'll give us a confidence level of low. Does that kind of clarify things a little bit? And if anybody has any more questions, just go ahead and ask away because someone else might be thinking it too. So all right. So this function just pretty much goes through all these previous 3 functions and completes it, creating a full pipeline for it. And then once it goes through everything, we'll have our answer, our confidence level, the documents used. So however many documents got validated, and then we have our documents rejected, says how many documents got rejected, and then we have fully grounded to determine if it's a fully grounded answer or not. Moving on, we have our corrective rag patterns. So self-rag validates outputs. And Troy, it might make a little bit more sense too once you guys get to the lab and actually start messing around with it. And maybe you might have to troubleshoot and you'll be able to understand it better. Uh, so, uh, all right, corrective rag patterns, self-rag validates outputs. Corrective rag goes further. It fixes problems when validation fails. So we have 4 different strategies for corrective rag. The first one is re-retrieval. When to use it is when there's a low relevance rate, and how it works is it expands search with more documents or reformulated query. The second strategy is query decomposition. When to use it is when when your query or question is too complex. And how it works is it'll break that complex question into sub-questions for and retrieve for each one. The third strategy is iterative refinement. When to use it is partially grounded answers. How it works, it regenerates focusing on unsupported claims. And then our fourth strategy is fallback response. When to use it is when there's no relevant documents, and how it works is uh, acknowledging limitations honestly. So let's take a look at the re-retrieval on low relevance. So when initial retrieval quality is poor, try again with modifications. So this function here, corrective retrieve, we're passing in a query, a vector store, and then uh, our minimum relevance. We're setting the default to 2, and we should get an output of a dictionary. So uh, this function right here just implements a corrective retrieval strategy where if the first search doesn't return enough relevant documents, it uses an LLM to rewrite that query and tries the retrieval again. So we have our first attempt. So the first attempt checks how many relevant documents were found. If it is more than the default of 2, then the system stops and it'll return the result. And if not, then it continues with the query correction. So again, for the first attempt, it goes back to that retrieve with validation. We can take a look at it again. So we're just retrieving the documents, uh, validating them or rejecting them, and then getting that validation rate. So then if the minimum relevance is less than 2, then it'll keep on uh, continuing on with the process on rewriting the query and trying again. So we specify a new prompt this time called rewrite prompt. So it says the search query, whatever we initially put in, returned poor results. Rewrite it to be more specific and likely to match technical documentation. Return only the rewritten query. So then we invoke our model with the usual model ID messages and the config. And then we have a new variable called rewritten query. And we're just getting that by parsing through that response and getting that text. So now we're going to try again with we're going to try a second attempt with that rewritten query. So we're calling that retrieve with validation function again, where we will validate the document or reject it. And then this part right here will just it combines the documents from both attempts and removes the duplicates. So we will return the documents. So it says combined, which is this list that we specify that all the documents get put into from the initial query and the second query. But now we're adding 2 to that minimum relevance. I was trying to think of why maybe we do that. So initially, the minimum relevance is relevant is 2. So I'm just guessing since we did 2 queries, that's why we're adding 2. Maybe if we did a third query, maybe we'll add 4 instead. Uh, so this part right here is pretty much saying, give me back the first 4 documents and get rid of the rest. And again, I was thinking maybe if there was a third retry, then we'll add 4 instead of 2. So it'll be 2, 2, and 2 for the minimum relevancy. So we'll get 6 documents instead. And then we specify our original query, our rewritten query, and then we're just saying that, yes, we used correction. Any uh, any questions on re-retrieval? So this is pretty much just, again, rewriting the query to make it more suitable. Next up, we have query decomposition. So complex questions often need to be broken into simpler sub-questions. For the function decompose query, we're just passing in a string. We should get an output of a list. And this docstring says break a complex query into simpler sub-questions. So uh, this function will just break down a complex question into smaller ones, and then it'll answer each of those sub-questions using the self-RAG pipeline. And then it'll combine the answers into one final response. So if we look at this prompt, it says break this complex question into 2 to 3 simpler sub-questions that can be answered independently. We pass in our query for our question, and then we add on some more to our prompt, return each sub-question on a new line numbered 1 to 3. So if the question is already simple, return just the original question. So if it's complex, it'll create it'll take that one complex question and divide it up into 3 sub questions. So see if there's an example at the bottom. So for example, if we had an original question that says, how do neural networks learn and what causes them to overfit? Then we only have 2 here, but we specified in the code we want 3. It says, how do neural networks learn and what causes neural networks to overfit? So each sub-question retrieves focused documents, leading to a more comprehensive final answer. Let's go back up. So we created our prompt. Now we're invoking our model. We're getting that result and parsing through the response. Again, the result is going to be those 3 questions if it's a complex question. And then this part right here, we'll just it'll parse through that response. That is a list. So the response is a list of the sub questions numbered 1 to 3. But this part right here will remove those numbering and put everything else into a list. And then next up, so the final output of everything over here is going to be a list with 3 questions, 3 strings without that number, or without those 3 numbers. Next up, we have a multi-step RAG function. And this just answers complex questions using the previous function. So it'll use decompose query. So docstring says RAG with query decomposition for complex questions. So we're calling that decompose query function, passing in our query, and again we'll get that list returned back. So 3 strings with 3 questions, and setting it to this variable sub questions. Are there any questions so far?
Hey Eric, it's Cam. Can you hear me?
Yep, I can hear you.
Is there like a function or a feature how does the LLM determine whether a query is complex or not?
Honestly, that's a more difficult question to answer. But, Uh, my best advice is to write a really good prompt so that it knows, uh, so I can give you the best answer possible.
Yeah.
Could also be just like semantically, like linguistically complex. Like if it can be reworded or not.
And so, okay, so the LLM, I see this as kind of like a gate, right? Like any query that comes through is going to go through this gate of like, is this complex or not? If so, conduct this, query to composition, right? And the LLM's making that decision, or is it going to go through this query decomposition no matter what? I guess the LLM is going to make that determination.
Yep.
Okay. Okay, cool.
And again, this is just this is a very bare bone RAG pipeline. I'm pretty sure there's ways to improve it. Uh, for example, going back to uh, what is it? The ground. Yeah, going back to that validate grounding function. This one is just checking to see if fully exists in the answer, so or the output of it. So you got to think of different edge cases and how you can improve it. This is just kind of getting uh, the concepts down uh, of of how you can implement self-rag.
But in both scenarios, we said LLM, you determine what grounded means, and then you break it into fully, partial, and then in complexity, you also determine what complexity means, and you give it back in the format that we're asking for.
What I'm finding when I'm looking into it, looks like there's three different ways that you can approach. Like one being um mm, so like prompt based. So like a if it's complex, doing a prompt that like does this question require multiple distinct pieces of information? And that's like yes or no. And so then that Boolean right there is like, is it complex or not? Would be, does it so you're basically having the prompt, fill in that. And then also you could also do just like search words. So like for complexity signals using like and also both compare difference between versus. So like a mix between those two. One's kind of more rule based, the other one's LLM based. Or you can also do something like token or clause counting. So increased count of clauses or length for a proxy.
Cool.
Yeah,
Thanks.
yeah, that's kind of what I was thinking too. That one approach where you would probably maybe give the LM or specify a checklist of what counts as complex to help it
Yeah.
determine uh, and get get that output, a better, more accurate output, I'll say. All right, any other questions? Yeah. All right, we're at multi-step rag. So again, we call that decompose query function to get those sub questions in the list. And then if the length of those sub questions is equal to 1, so that probably means that it found that original query to be not complex and thinks that it is simple, then it'll just go ahead and go to the self rag pipeline straight away. Otherwise, it'll continue and we create a sub answers list and an all docs list. And honestly, I was thinking, I don't know why this is here. I don't, this part right here doesn't even really need to be included, but let's continue on. So it'll go through a loop within the sub questions. And we'll, for each question, we're going to be calling in that self-rag pipeline and passing it within there, as well as the vector store. And for those, for whatever we get returned, it'll append the question, the answer, and then the confidence level. So after we go through that loop, we have a new prompt called synthesis prompt. So the synthesis prompt asks the LLM to combine the answers. So it says combine these answers into a comprehensive response to the original question. So we give it our original question, and then we give it our sub answers using this line of code. And then we leave room for the LLM to respond under synthesized answer. So we pass in that prompt to Bedrock, get our response, and then we return the answer. So we're parsing through the response to get that text. We have our, for our sub questions, we have our sub answers. And then it's saying, we're just pretty much specifying if it's been decomposed or not. So I think we looked at this example already, but again, the original question, how do neural networks learn and what causes them to overfit? It gets decomposed into how do neural networks learn, and then what causes neural networks to overfit. Each sub-question retrieves focused documents, leading to a more comprehensive final answer. Any questions before we move on? All right, so for CI/CD for RAG systems, self-RAG validates at runtime, CI/CD validates at development time, catching regressions before they reach production. So why CI/CD for RAG? Without CI/CD, manual testing is required after changes, broken prompts reach production. We have a problem of it works on my machine, but maybe it doesn't work on another machine, and there's no quality history. With CI/CD, there's automated testing on every push, regressions caught immediately, consistent test environment, and it tracks quality over time. Over here in our next code snippet, we have a bunch of different RAG test cases. So for the ID, it's just the test identifier. For query, it's our question sent to the RAG system. Expected keywords is the words that should appear in the answer. Expected confidence is the expected confidence level for it. And then category is just the type of question. So this first one says, first and second one are technical. And then this last one is out of scope. So it's not even talking about anything technical related. It's just asking what the weather is. And then we finally have a function called test rag quality. It'll test rag answer. It'll test rag answer quality. So it just runs the test against the rag pipeline that we created. Over here, we have imports starting out within the function. So we're importing that self-rag pipeline and then the vector store. We create a variable called results to and set it to an empty list. After that, we have a loop that goes through each case in the rag test cases. So this first part right here, it just sends the query to the self-rag pipeline, the query from the case to the self-RAG pipeline and also passing in that vector store. And then it'll check the keywords. So it'll check if the keywords are found in the answer and calculates a percentage of how many keywords were found. So that's what this loop is doing. And then we have check confidence. So we have the confidence match. This is so this is just this portion right here is just checking the confidence level and if the test passed. So if the keyword score is over 0.5 or over 50%, and then the confidence match, hold on, let's go back. Confidence match equals result confidence. So if the resulting confidence from when we pass it to the self-RAG pipeline matches the expected confidence from the test RAG case, it'll get set to confidence match. And then over here, the criteria for passing is if the keyword score, so the amount of times that the keywords appeared is over 50% and the confidence matches, then it'll pass it.
Eric, can I ask real quick, what
Mhm.
determines the keyword list?
The keyword list.
Yeah, how does it know what a keyword is?
So the keywords are coming from the expected keywords over here, and then
Oh,
to
thanks.
actually get the score, it's going through this loop right here. So let's actually go through it. If expected keywords in the case, so this is getting the result from the self-RAG pipeline, looking for the answer, setting it to lowercase, and then keywords found equals the sum of those keywords. So one for keyword in case, expected keywords. So it pretty much is comparing what it got back from that. So the result from the self-RAG pipeline, and then taking a look also at those expected keywords and calculating uh, how many times it is shown in there. And then to get the keyword score, it'll say keywords found within that result, and then we'll divide it by the length of that expected keywords. That's how the keyword score is calculated.
Yeah, thank you. I got hung up on BM25 from yesterday and, keywords in that use case. This is different because we're feeding the keywords, so thank you.
Yep, no problem. So then, so if everything passes, uh, so it'll say if it's passed, and then we'll append those to the results list. Where there's a key difference. So there's result and then results. So results is the list, and then result is what you get back from that self-RAG pipeline. All right, and then so we're appending the ID, the case ID, whether it passed or not, the keyword score, and then the confidence match, and we're appending it to that results list for each case. this part right here is just saying if anything uh it'll it'll stop the execution if any of the tests fail, pretty much is what this is saying. And then this is just calling that test rag quality function. Any questions before we move on? Anything I can clarify? All right. So for GitHub Actions workflow, uh, is just you guys have seen this before, so we're naming this workflow test rag system. Whenever we push to the main branch or create a pull request to the main branch, we want this job to run called test. It runs on Ubuntu latest, and then here's the steps. So we'll check out the code, set up Python, install dependencies, and then run the reg test. So we're running that file test rag.py, and we have our env and credentials to help with that. And
Should
then
have made that
finally,
global.
what was it?
The env file. I'm sorry, the env definition. It's so important. Should have made it global, but because if you place an env designation at the top of the GitHub Actions files, it makes it global in scope, so that all the other all the other steps can use it.
Mhm.
But it would have been smarter to make that one global, I think.
Yeah.
Yeah, I think that every time I use the echo for like each EMV virtual environment,
Mhm.
I never do it.
Yeah, remember there's multiple ways to do it, but this is just for like a quick demonstration. So this got put in right here since it was just being used to represent running that rag test. And then we have upload test results. So it's saying always, and then we're just uploading it. We store AWS credentials as GitHub secrets, never in code. So you add it on GitHub. And then we have our workflow triggers. So what we just went over. And then now we're getting into conversational memory. So the memory problem, what is overfitting? It responds overfitting occurs when a model memorizes training data. Next query says, how do I prevent it? But now the RAG system doesn't know what you're talking about. It says, I'm not sure what you're referencing. So that's why memory is always good to implement. So for simple memory implementation, we have a class conversational rag. We initialize the vector store history and then the max history of, so however many conversational turns we could have in the history. So it's set to 5. And then we have a method called chat. And we have we set a variable called history text to empty strings. And this portion right here just takes that history and it'll combine everything and sets it to history text as a string. And then we have retrieve documents. So again, we're calling that retrieve with validation function, setting it to retrieval. And then we have our context for the components inside those validated documents. And now we create our prompt. You are a helpful assistant. Use the conversation history and context to answer. We provide our conversation history. So that history text from this line right here. And then we have our context. And then we pass in our current question and leave room for the LLM to answer. So we invoke our model, set it to response. We parse through that response to get the text, set it as answer, and then we save it to the history. So we save the query and then the answer. And then we also have a method called clear history. It'll just start a new conversation and delete the history. Memory aware retrieval. So we have contextual retrieve. It just checks to see if the current question references previous conversation turns. If it does, it rewrites it to be self-contained using an LLM. So self-contained meaning that the query can be understood on its own without needing to look at previous conversation turns. So we're passing in query, the history, and then the vector store. Docstring says retrieve use both current query and conversation context. So if history exists, expand query with context. So this is so it just checks to see if uh the history exists and looks at the last uh most recent conversation turn. That's what this -1 is saying. And we're setting that to last exchange. We create a prompt called expansion prompt. Given this conversation context, expand the current query to be self-contained. We have our previous question. So last exchange query, and then previous answer, last exchange answer, and then the current question. So if the current question references the previous exchange using words like it, that, this, rewrite it to be standalone, otherwise return the original question. And then we leave room for the LLM to answer under expanded question. And then we invoke our Bedrock model. And then after that, we get our response. We parse through it, set it to expanded query. And then, so, oops. So let's go back to this prompt real quick. So if in the history there was a question, what is RAG? And then our current query says, how does it work? The prompt instructs the LLM to rewrite to how does RAG work, is what this prompt is doing. And then if there's no history that exists, it'll just set the expanded query to the original query that we had. And then finally, the vector store gets searched using the expanded query and returns the top 3 relevant documents. Here we have another example, history. User asked, what is overfitting? Current query, how do I prevent it? Expanded query, how do I prevent overfitting in machine learning models? Now retrieval finds documents about overfitting prevention, not random prevention topics. Memory summarization. So long conversations consume tokens, summarize old turns to reduce costs. So this function right here will just summarize the conversation history in a way that saves tokens so that it can reduce the cost. So this portion right here is saying if the conversation history has 3 or fewer turns, it's short enough to include fully. And then if not, then we specify the old turns and then the recent turns. So the old turns is everything besides the last 2. The recent turns would be the last 2. And then old text just concatenates the older conversation into a single string. So that's what this portion is doing. And finally, we specify a summary prompt, summarize this conversation in 2 to 3 sentences, keeping key facts and topics discussed. And we pass in that string of old text. And we leave summary section for the LLM to respond under. We invoke the Bedrock model. We parse through that response, set it as the summary, and then recent text. We just combine we combine the summary with the recent turns, and then we return earlier. We return the summary and then the recent text or the recent history. So this part right here just puts everything together. And for summary, again, we have 1, 2, 3, 4, 5, 6, 7 patterns: relevance validation, grounding validation, re-retrieval, query decomposition, CI/CD testing, conversational memory, and memory summarization. So for relevance validation purposes, filter relevant documents when to use it. Always, it improves precision. Grounding validation pattern, it verifies that the answer is supported when to use it. High stakes applications. For re-retrieval purposes, to fix poor initial retrieval when to use it when relevance rate is low. For pattern query decomposition purposes, handle complex questions when to use it. Multi-part questions. Pattern is CI/CD testing purposes, to catch regressions when to use it. Every code change. And then pattern for conversational memory, it enables follow-up questions when to use it. Multi-turn interactions. And memory summarization, it just reduces token costs when there's long conversations. Self-RAG and corrective RAG transforms your system from generate and hope to validate and verify, combined with CI/CD automation and conversational memory. You have the foundation for production quality RAG. And again, just a side note this is just there are better ways to incorporate this and improve on it. This is just to so that you guys can get the different concepts. Are there any questions? All right. If there's no question, go ahead, Troy.
The vector database that we set up to store the history, this class is firing off, this conversational RAG class is firing off when one user starts to engage with it. This setup, is it good for multi-users simultaneously, or the code that we have here needs to be limited to one user at a time? I guess my question is, like, in the vector database, how are we, delineating multiple users at one time?
So from so we have memory, but one way to incorporate that I would say is to create different sessions. So go ahead. You have something to say,
Oh
Keith?
no, I was just about to say the same thing, but go ahead. Sorry.
Yep. So
Yeah.
I would create different sessions in order to do that, because this is only implementing memory. So maybe yeah, sessions would be the way to go.
Okay. Thanks.
Yep.
Yeah, because the same thing with Mem0 though, it requires you to provide like a session or a client ID.
All right. If there's no questions, let me stop the recording.